Earlier, we looked at Newton's first law, or the law of inertia, and then Newton's second law, or F equals ma, and now we want to look at his last law of motion, or Newton's third law. Newton's third law deals with a fundamental characteristic of all forces, and that is that forces always come in pairs. Newton was first to realize there is no such thing as an isolated force, existing all by itself. Let's now state Newton's third law of motion. Whenever one object exerts a force on a second object, the second object exerts an oppositely directed force of equal magnitude on the first object. The third law is often referred to as the action-reaction law because it is often quoted as, for every action or force, there is an equal but opposite reaction. Let's see how we can apply Newton's third law to an action-reaction pair of forces between two objects and calculate their respective accelerations. Consider the figure below, where an astronaut pushes on a spacecraft with a force of plus p. According to Newton's third law, the spacecraft must push back on the astronaut with an equal but opposite force, or minus p. Suppose the mass of the spacecraft is 11,000 kilograms, and the mass of the astronaut is 92 kilograms. In addition, assume that the astronaut pushes with a force of p equals 36 newtons on the spacecraft. We want to find the acceleration of the astronaut and the spacecraft. Consistent with Newton's third law, when the astronaut applies a force of positive 36 newtons to the spacecraft applies a reaction force of minus 36 newtons to the astronaut. As a result, the spacecraft and astronaut accelerate in opposite directions. You might have initially thought that since the magnitudes of the two forces are equal, the accelerations of the two objects would be equal as well. However, that's not the case as the astronaut and spacecraft have different masses. According to Newton's second law, the astronaut will undergo a much larger acceleration than the spacecraft, since her mass is so much less. Using the second law, we calculate the accelerations to be equal to positive 0.0033 meters per second squared for the spacecraft, and minus 0.39 meters per second squared for the astronaut. Even though the magnitude of the force on each object is the same, the acceleration of the spacecraft is much less due to its larger mass. We should note that each force in an action-reaction pair acts on a different object. So if we were to draw the free body diagram for the spacecraft, for example, only the force plus p would appear in the diagram, and not minus p, which acts on the astronaut. Here we have shown an example using Newton's third law to analyze contact forces between two objects. However, the third law applies equally well for non-contact forces too, such as gravity. Imagine an astronaut in orbit around the Earth. The Earth exerts a force on the astronaut, pulling her toward the center of the Earth. And by Newton's third law, the astronaut pulls on the Earth with an equal but opposite force.